Thank you very much for your time today. Welcome to Spark and AI Summit. My name is Antoine Amend, and I'm the Technical Director for Financial Services at Databricks. Today, I want to walk you through the modernizing a risk management practice using Databricks, using cloud-based technology, with the example of enabling a value at risk calculation onto our platform. Prior to joining Databricks, I was leading an AI practice for a large UK retail bank, and I've led multiple transformations. That always comes down with getting the data right. In this case, I want to demonstrate how to leverage Delta Lake to bring data in a timely and reliable manner. How you can scale your Monte Carlo simulation using the flexibility of cloud compute with Apache Spark to run millions of Monte Carlo simulations in parallel. How do you bring model delivery, model risk models in a way that is transparent enough for risk and regulation using Delta Lake and ML Flow? How you can then enrich and augment the information so that as a data analyst, as a risk analyst, you will be able to slice and dice your value at risk on demand, enabling an intraday view of your risk facing your business to serve multiple use cases, multiple analyses. And that's the whole point of a data transformation, is really shifting the lens we see data as a cost to an organization to an asset to your business, and embracing the versatile amount of data to serve multiple use cases, bringing that level of interactivity to your risk-related data. With this series of few notebooks, we'll be enabling a value at risk calculation using our models and surfacing those models through a simple SQL-based functionalities, so that as a risk analyst, you can be slicing and dicing and aggregating your risk exposure across different countries, different industries, different segments, and have a more descriptive view of the risk facing your business. Before we get started, a few links that I'm sharing with you. So everything we'll be covering today has been sent on a couple of blog posts available here, as well as the different notebooks we'll be covering today, from a market ETL to a model development, Monte Carlo aggregation, and backtesting are available and publicly available to you. So let's get into the platform. So if you're not familiar with the Databricks environment, this is what a platform will look like. Your workspace will contain all your different notebooks. You'll get access to all your different data, creating different clusters, maintaining all your models into one single source of truth, which is the ML registry, and tracking your experiment with ML Flow. So value at risk, this is what we eventually want to demonstrate today. So Delta Lake, ML Flow, Apache Spark working together to bring that more agile and forward-looking approach to risk facing your business. But value at risk, in a sense, is really about measuring the potential loss at a specific confidence interval and a specific time horizon. How much can a business can afford to lose on their investment portfolio, given a certain 95 or 99% level of confidence? And for this, they will be running Monte Carlo simulations at scale to simulate prices. And if you get this example here with the synthetic instrument, I want to start generating all the possible outcomes, all the possible futures, to generate what my investment could be tomorrow or in a month time from now. And that will be creating those so-called random walks or Monte Carlo simulation that are driven by historical data. How much volatility did I observe in the last 90 days to create the statistics to help me create those random walks? But if I flip that graph and get the distribution of possible returns, this is what my value at risk will look like. I get the 5% quantile or the 95% confidence, and that gives me the best of the worst and event that may happen within a time horizon and a confidence interval. This is a really simplified example using only one synthetic price. In reality, banks may have hundreds of thousands or tens of thousands of different instruments across different books, across different portfolios, and you may not need to generate Monte Carlo simulation for each and every single point price, but more for market conditions. So you will need to generate Monte Carlo simulation for market condition, and then build a model that could predict the instrument return for each of your instruments in your portfolio. So let's get into the world of ETL and getting your data that is analytic ready. So in this case, I create a synthetic portfolio made of 40 equities in a Latin American portfolio. So across Chile, Colombia, Mexico, across different industries like banks, beverage, electricity, mining, and so on and so forth. I can store that simple portfolio into a delta table that will be stored in a stored format as delta, and that contains my input parameters, where I will be reading stock data and generating my Monte Carlo. In real life, you may be streaming your data directly from a change data capture from your mainframes or source system. In this case, because I do not have access to such an environment, I'm simply using Yahoo Finance and downloading each of these 40 instrument historical data using a pattern that you will see a lot in this demo called the pandas UDF. So everything that you will see within that pandas UDF function is plain old Python. So you can group by a specific parameter and apply plain old Python that will return my data as a pandas data frame. In this case, if I have 40 instruments, I want to leverage Yahoo Finance, which is a third-party library that I've just installed on my cluster, to download the last 2 years worth of history for all the specific ticker in my portfolio of South American portfolio. So in this case, grouping by a specific parameters and then applying my pandas UDF, I can start overriding into my delta table that contains all my stock for every single day, the open, high, low, close, and volume. I can create a simple widget here through the use of dbutil so that my notebook will start getting more interactive. I can select for a specific equity and access a specific instrument. In this case, I'm accessing this instrument here and can uncover the effect of coronavirus around end of Feb, beginning of March. As I was saying in the introduction, it's not about generating prices, but generating market condition. So I assume for that experiment that my portfolio is highly predicted by those 5 market indicators, such as the SP 500, the New York Stock Exchange, the crude oil, treasury bond, the Dow Jones, and I'll be applying exactly the same of using data coming from Yahoo Finance and computing log returns, computing daily returns. So I can apply a simple window partitioning on top of my entire data frame and store my result into a delta table. So that will bring me the distribution of all the possible historical return for that specific stock. At this point, I can start directly applying historical value at risk, but I don't want a historical VAR when the end goal is to generate all the possible futures, so we'll need to simulate those market conditions. Something worth mentioning in the world of delta lake is we bring consistency and reliability to your data, but also reproducibility. So everything on delta will be tracked and enables you to travel back in time to a previous version of your data. So as I can describe my specific table has multiple versions, and I can access my data at that specific version as of version 1 or as of 1st of June 2020. We can show us how to bridge the gap between streaming and batch by, instead of reading as a table, you read as a stream and the format remains exactly the same. This will be particularly useful when reading directly from a change data capture instead of Yahoo Finance. So with all our data in one place, then we can start creating a model experiment. We can start creating our predictive model that will, given specific market condition, will generate my investment return for each and every single equity in my Latin American portfolio. This will be using some date parameters, such as this is when we started to train our model. Our model, we say, will be predicted by those 5 different indicators, such as the SP 500, the Dow Jones, and so on and so forth. And I want to ensure full reproducibility, as I alluded in the previous notebook, by accessing our information at a specific point in time, so that my ML is reproducible. Given that my market indicators easily fits in memory, I want to get into the world of pure native pandas. So converting from a PySpark to a pandas data frame using a simple 2 pandas. and evaluate my different market factors. And here, applying simple data science, showing that I do not have any correlation. In fact, if you look at my SP 500 and Dow Jones are highly correlated, but let's assume for the purpose of that experiment that they are not. They are not correlated, and they are highly predictive of my stock returns, and therefore good candidate for my model development. So I will be training a model for each of my instruments, and I have 40 of them. So the first will be to join my, my market conditions based on dates, and I will be building my input vectors. Those will be my market condition for the different instrument that I showed, and that will be my target variable, being the instrument return. So now with those data sets, I can apply again the same pandas UDF, group by my instrument, and in parallel, train a model. And training a model, I want to get something really simple here, and we can make that as complex as we want, but the principle remains the same. I want to apply a simple linear regression model using, in this case, non-linear transformations, as our market may not be following a linear distribution. So in this case, I want to train a simple model, a linear regression model using the stats package of Python, and aggregate those weights into one matrix that will be written from my trained model, and that again fits in memory. This matrix will contain for each of my 40 instruments all the different coefficients from my linear regression model that I can use in a predict function and look at the mean square error. So having a sense of how my model works against those 40 instruments, and show the predictive value. So in blue will be the actual stock return of Ecopetrol, and in green would be given the market condition at the specific point in time. Those have been my predicted outcome for the same instrument, Ecopetrol. Again, it could be really more complex, but the principle remains the same. And I can register my model, logging all the hyperparameter used, as well as the version of my delta table used for market condition, as well as for stock, storing all those evidence alongside my model, so that I will bring all the technical and business context for my model risk management practice, part of my enterprise risk management framework. So these are all my different models trained at different points in time that contains all the metadata that I want. And I can show you quickly that as long as you can express your business logic into the world of Python, you can benefit from an ML flow and ML registry perspective by packaging your model as a machine learning model. But a model in a bank may be quite broad and maybe a simple rule-based to a simple stats-based model up to a state-of-the-art AI. Still, you can be using ML registry and ML flow for that purpose. So with our model, we can start scaling our Monte Carlo simulation. So we get some input parameters. And what we want here, we want to get the last 90 days of historical data so that we can compute a volatility and extract those statistics to predict possible outcomes. We want to train to enable 50,000 simulations for each of my 40 instruments. The industry standard will be anywhere from 20,000 to 30,000. So in this case, I want 50,000, but nothing stops me from scaling this out then to 100,000, to 1,000,000 simulations if I desire so, given the flexibility of cloud compute and given our job that is highly parallelized. We specified the path where we stored our model in the previous step. So given that we provide our model with a name, and then we can use ML registry to retrieve my production version or to retrieve my staging model at a specific version. We retrieve the different models and data as this specific point in time in the last 90 days and create some statistics around those historical 90 days historical of market condition by computing volatility. And the volatility is nothing more than just the standard deviation of actual returns. In this case, because we are talking about 5 different instruments, I will be getting the covariance matrix to build what's called a multivariate normal distribution. If all my instruments are following a normal distribution, the superposition of each will be a multivariate normal distribution that I want to sample point from. So in this case, given specific statistics, let me extract a point from that distribution that will give me some generated market condition. Something worth mentioning that is true everywhere, but particularly challenging in the world of big data and distributed programming, is you want to create a seed strategy to generate pseudo-random number, where each trial needs to be independent from the rest. And each trial, should you need to call that twice, or in our case, 40 times, needs to be consistent. Every time I ask the same trial to be reproduced, I need to end up with exactly the same market condition that I can use across my different models. In this case, you can create a seed and fix that random number to that specific seed so that your experiment becomes reproducible and independent across the different trials to avoid any autocorrelation issue. So now with our seed strategy, we can distribute our seed strategy and make sure that each executor in our cluster will be responsible for exactly that number of simulation. By creating this and leveraging the parallelism that we have in our cluster, we can ensure that if I have a 100 nodes cluster, I have 100 nodes that are working at the same time. And you don't want to wait for one simple executor to wait when the other one are idle. So I want to fully exploit the parallelism that I have. So I retrieve my statistics, I broadcast my different statistics to my executor, and then I can send some seeds to my executors who will be each responsible for running those Monte Carlo simulation through, again, a Pandas UDF. The Pandas UDF is here for each seed that, as I'm an executor, I'm responsible of. I will be generating market condition, and I will be then, for each of my model, predict my instrument returns. That gives me a really large table for every single day, for every single ticker, for every single trial ID, I get my generated trial outcome. So if I'm interested in a specific slice of data coming from all those different countries or industry, I can easily group by a trial ID to compute my portfolio generated outcome and select eventually my value at risk. This is what we mean by having a versatile approach to your data, and data being an asset to your business instead of a cost. We want to start enriching that with the different industry and country and additional metadata, so that as a data analyst, as a risk manager, you can slice and dice your data on demand and not restricted to a specific use case. So if today you're being asked to check what's your risk exposure to Italy or to this country, or what's your risk exposure across all your oil and gas producer position, then you will be able to aggregate that information on demand. And this is what we want to do in stage 4 here. So in stage 4, I want to leverage the information that I had from my previous, my Monte Carlo simulation table. And I want to start doing at the daily value at risk calculation. So computing a point-in-time value at risk, where I can create a simple widget, again, as demonstrated here, available in my Databricks environment to bring that level of interactivity. And if I want to specifically to extract the value at risk as a specific point in time, then I can filter my full table for a specific date and aggregate by my trial ID, by my market conditions, aggregate my portfolio returns, and get my distribution. The value at risk will be my 5% quantile for 95% confidence. And this is it. Again, really easy. I extract that specific slice at that specific point in time to apply my 5% threshold, and this is my value at risk across my entire portfolio. So we did that on demand without necessarily having to aggregate at write. We can aggregate at read. But if you've spotted that, I was collecting all my daily data in memory because I have only 50,000 operations. And I was only doing that for one specific day. And this will be highly inefficient to collect all my possible trials day in memory when running my value at risk. So I want to have a smarter strategy. And in this case, I want to leverage the fact that my value at risk has been designed to work on the worst N event only, where N is really small. why should I collect the entire distribution when I'm only interested in the best of the worst N events? Given 50,000 simulations, if I want my value at risk 99, then I'm only interested on the worst 500 events. So why should I get my entire distribution? And why can't I use a simple user-defined aggregated function where each of my executors in my network will be responsible for giving me the worst 500 events, and eventually I take the best of the worst 500 events. That is driven by N, being driven by the confidence level as well as the number of records. And given that user-defined aggregated function, I can then register into the world of SQL. So I have a new function called value at risk that I can use on SQL. So given this 57 million records currently in my Delta Lake of Monte Carlo simulation, I can apply my value at risk aggregating my data across my entire portfolio on demand. This, through the use of simple SQL that will take only a few seconds to run, will uncover the COVID virus effect around Feb and March this year. So this is already fantastic that we've been able to run a value at risk calculation together on demand without having to rely on daily processes. But it may not be enough. In some cases, you want the risk exposure to different countries, to different industries. But because we have this now information available on our Delta Lake, enriched with industries and countries, because we now have this user-defined aggregated function that is available through the use of simple SQL, nothing stops us from having a more granular view of the risk facing our business across different countries. And in this case, you can see that most of my value at risk for my Latin American portfolio is mainly related to the activities in Peru. So I may wonder what's happened in Peru, and therefore aggregate this time no longer by industry, but selecting for Peru and aggregate that by different segments. And in this case, I could see that after coronavirus, COVID virus, 60% of your risk exposure in Peru is down to mining industry. And I'm not a risk analyst, and I don't know anything about mining industries in Peru, but I've been able to uncover that by being a more reactive and descriptive to the value that I have by bringing this agility and this interaction with my risk-related data. And in fact, just simply Googling some articles, it seems that Peru is indeed a center for gold, copper, and silver, and has been the biggest hit because of COVID lockdown. So we can start looking at the use of alternative data. Could have we detected that prior to our value at risk calculation? And again, this is about augmenting the information that we have through the use of alternative data. So we'll go really quick on this one. I'm using news articles coming from a website called GDEL for the global database of event, location, and tone. And I want to access all this information on just downloading from a simple bash, but then moving my data from a bronze table to a silver table to a gold table, where I will be containing all the different GDEL information and then filtering only for things that are related to my portfolio and then only detecting potential trends. So respectively bronze, silver, and gold. So I'm only interested in few countries, in few industries, and I get every single themes as well as the tone, the sentiment across the different country for every single 15 minutes. So detecting trends then without really getting into too much complexity here, I want, in this case, to have a simple moving average. You mean the 7 days moving average and the 30 days moving average, and you can bring that, that visualization onto our platform here. So if I get the different visualization, the different day, the trends, and the total, I can uncover directly the different trends here. So it looks like on the 6th of February, 3 weeks before my value at risk started to degrade, I could have detected the trend on any mining industry related articles in Peru. So we could have moved from being a descriptive to a more predictive approach. And this is what I give you as an information here, this fantastic white paper where financial news could predict stock market volatility better than a close price, and how we can incorporate this information that we have from the outside world into a world of value at risk. And last but not least, then, it's when we have a model, we have to comply with risk and regulation. We have to comply with Basel I, Basel II, Basel 2.5, Basel 3 frameworks, and we have to get back to regulators with a backtest of our model over the last 250 days. This is a usually painful exercise, but hopefully easier given that we brought that agility, that on-demand aggregation, so that I can register my aggregated defined function as I was showing you before, enable that value at risk calculation through the use of simple SQL, and do some as of join what my value at risk was at that specific point in time, so that I will be able to extract breaches. I will be able to extract anytime my investment returns, my P&L, was exceeding my value at risk over a period of 250 days. So having a window function that operates in the last 250 days and being able to detect all breaches. So this is this end goal here, what we wanted. So we've been able to access my value at risk, the evolution of my value at risk calculation, and we can see the COVID effects in March. We can see in green the volatility of my observed portfolio, and something quite important twofold. First, they have now a lot of breaches that I need to comply back to regulation. Second of all, the value at risk decreases, but does not decrease as fast as my volatility increase, because we still have a 90 days lag. We are still looking at this from a backwards-looking approach of historical data instead of a forward-looking approach. And how, by moving to the world of alternative data, by moving to the world of agility in your model, can you shift that to the left and have a more reactive, predictive, and prescriptive view of the risk facing your business? So now we have to report back those breaches to regulation. We have between 17 and 18 consecutive breaches that, in fact, most of the banks are experiencing today. Most of the top-tier banks are reporting breaches in their value at risk, despite stressed value at risk or incorporating worst-case event that happened in the past. They are still breaching those rules by risk and regulation. So modernizing will be by being back in control of your data, being back in control of your processes, having a more agile, interactive, and on-demand view of your risk, and augmenting that information with new information as they unfold. So with that in mind, I've covered what I wanted to cover with you today. So the value at risk calculation, we have the blog post, the notebooks, and I'm available for any question that you may have. And it's been a really, really pleasure covering this today with you. Thank you very much.